All right. Hello. So, yeah, I'm going to talk about borrowing. So borrowing is a language feature that's basically a response to all the memory safety bugs that affect languages like C and C++. And it's become super popular lately because of Rust, basically. And I want to start with a quick introduction to what borrowing is, just for people who aren't familiar with it. So in Rust, you can allocate memory for the number 7, for example, and you get a pointer to it. You can store that in a variable x. And now let's say you want to pass x to both arguments of the function foo. So the first thing that happens is that x is moved into the first argument, but this means that foo now owns the value of x, and the variable x can't be used anymore. So we mark x as moved. So when you get to the second argument, Rust will give you a compile error because we can't use x twice. So the benefit of this is that it rules out some problems that happen at runtime. So for example, if two different parts of the program think they have the pointer, one of them can free it while the other is still using it. So you get a use after free error dangling pointer. So this will rule that out. But only ever being able to use the variable once is a little too restrictive for most programmers. So Rust lets you borrow instead of moving. So now you can have multiple aliases to the same place in memory. They're all pointing to the same place, but no one can free it. So there's no way a dangling pointer could happen. And the ampersands just mean that it's a read-only or immutable borrow. And because it's a borrow, after foo returns, you automatically get x back. And now you could do whatever you want with it. You could free it, you can borrow it again, you own it. Sometimes you want to use a variable more than once, but you also want to be able to mutate it. You don't want it to be read-only. So when you immediately borrow x, you're still not allowed to have multiple aliases. So x is still deactivated, like when you move it. But unlike when you move it, you automatically get x back after foo returns. So both these cases can be summed up by this motto, aliasing XOR mutability. So memory safety is guaranteed when you either have many pointers aliasing a single location or the ability to mutate that location, but never both at the same time. So how does Rust know when to give you back a variable that was borrowed? And it uses lifetimes. So when you borrow something, the compiler decides how long that borrow is allowed to live for. So in this example, the borrow lasts until the end of the scope. And if you try to mutate x while an immutable borrow is still active, it will be a compile error. But you're allowed to use the borrow in the scope. And after the lifetime ends, the assignment that didn't work before now works because the borrow is dead. And so a few years ago, Rust added this feature called non-lexical lifetimes, or NLL. And it basically just gives the compiler more flexibility in determining how long a lifetime lasts for. So for example, if we have this variable x here, which is an option type, and we match on it, the lexical lifetime would normally be until the end of the scope, the parent scope of the match. So in the sum case, you could bind the value behind the sum and mutate through it, mutate through the borrow. But in the none case, you can't really, there's nothing to bind. So you might want to try instead to mutate the original variable. But that's not allowed because it's in this blue lifetime area. So that the borrow is still alive, x is still deactivated. But with NLL, the compiler can choose to end the lifetime early. trade-offs that every project has to make. But the trend is that borrowing research tends to be heavily colored by specific industrial languages like Rust. And it can be hard to generalize or reuse this work in the context of other languages or systems. And like a widely accepted language-independent tool for studying borrowing seems to be missing. Or in other words, there is no canonical borrow calculus. And by canonical, I mean something that wouldn't look out of place if it appeared in types and programming language in TAPL, for example, if TAPL had a chapter about borrowing. So here's like a wish list I have of what I want a borrow calculus to do. I wish it would capture the essence of borrowing without getting bogged down by implementation details of specific languages. It would be nice if it could be extended with new features and used for different applications without too much difficulty. So I basically want the Platonic ideal of borrowing. You know, some very abstract notion that can be instantiated in different contexts. For example, if you want to study polymorphism, you might start with system F, which is a pretty minimal extension to SDLC. And it seems like there's not really anything like that for borrowing. And speaking of system F is on the lambda cube, and we think it'd be nice if there was something like the lambda cube or the complexity zoo, but for borrowing. Because borrowing is really many separate features, and you can dial up the complexity or dial down the complexity depending on your use case. For example, when you think of Rust-style borrowing, it's actually a bunch of different features that are all sort of working together. So you could break it down into mutable and immutable borrows, lifetimes, lifetime polymorphism, and non-lexical lifetimes. But you don't need all these features at the same time to have a language with borrowing. You can actually get away with just having immutable borrows without even lifetimes. And this corresponds to the system in the temporary read-only permissions paper that I mentioned earlier. And we call this downward only, and I'll explain why we use that name. You could draw different boxes around different features. You could just take the left side and get like a purely functional borrowing system. We're working on a calculus that includes all of these features except for non-lexical lifetimes, and we also build up these features incrementally, starting from downward only and adding features one by one. So you can imagine drawing all these different boundaries. You can imagine adding new boxes representing new features that go beyond Rust. And you end up with this classification of many different possible borrow calculi. And we call this the borrow zoo. We want a taxonomy of borrowing calculi, essentially. So here's what we're working on. This is work in progress. We haven't published yet, but we hope to soon. So we have a core calculus for borrowing that's designed to be extensible and also application agnostic. It's a calculus that contains just borrowing, like no other features to distract from the borrowing. And we extend linear SDLC because we need that aliasing discipline. It's mostly compatible with Rust. Not exactly Rust, but we try to follow the general idea of how Rust borrows work. We can model some, but not all, unsafe code, for example. We don't support NLL, which I think is the biggest difference, because we feel that NLL is a bit too complex relative to the expressivity increase it brings. And the relationship between lexical lifetimes and NLL is also a little fuzzy. So some cases of NLL can be desugared into lexical, and other cases can be just avoided by rewriting your program. It might end up being slightly less efficient after rewriting, but for purposes as a core calculus, where we aren't as concerned about verbosity or performance issues, but we are concerned about simplicity and elegance, then these are acceptable trade-offs for us. So yeah, we have 3 levels of abstraction. We start with a type system at the very top. And below that is a separation logic modified for borrowing, which the type system is proof sound with respect to. And below that, at the bottom, we have a semantic model that the separation logic is proof sound with respect to. And our soundness includes these standard memory safety properties like no use after free, aliasing X immutability. We also have reclamation safety, so there's no memory leaks. And our language is actually also terminating if you don't add loops or generate recursion. Okay, so I'm going to talk about this. I'm going to start from the very top with the type system. So I'm going to start with an example. So this program allocates integer 7. It's implicitly boxed. X is actually a pointer. And if we want to pass x to the same function twice, like in our first example, we can start by borrowing it. And there's this let thing is just a call by push value thing that you can ignore it for now, but I'll sort of explain what's going on there. So the scope with the braces is where the borrow of x is allowed. And because all variables are linear, even including the borrows, we have to duplicate it first. But it's OK because it's an immutable borrow, so it can be duplicated. And then we pass both copies to foo, and we can drop it afterwards. So this is sort of resembling the Rust example from earlier. And we can also do this with a mutable borrow. We can't copy it, but we can split it because we're borrowing a pair. So we can split it into, we borrow the whole pair, and then we split it into a borrow of the first component and the borrow of the second component using this split primitive. And then we can pass it to our function and drop it. So let's look at the syntax and how we're defining the type system. And I'm going to start from incremental. I'm going to start from the very simplest model and add features one by one. So this is downward only. And we're starting from linear call by push value lambda calculus. So call by push value means we partition into value types and computation types with thunk and ret to go between them. And we use call by push value because it makes our calculus a bit simpler and more elegant. But a call by value version is also possible, and it's not too much trouble. So we add a borrow type and a borrow value, and some operators for working with borrows that I've already shown you. And we have 2 typing contexts. We have an owned context, and we have a borrowable context. So gamma is treated linearly, but delta is duplicable because we just have immutable borrows. And they have to contain different variables. So if you want to type, let's start with like a naive first attempt at the typing rules and see what happens. So if you want to type this borrow x value, then first of all, you can't own anything. And also, x has to be in delta with type v. So this is saying that it's in the context that says it's eligible to be borrowed. And if we want to do sequencing of 2 computations, first we split the context, like in linear languages. And so in a normal linear language, you would give gamma 1 to C1 and gamma 2 to C2. But our language is not a normal linear language, and borrowing is actually a relaxation of linearity. So we can actually give both gamma 1 and gamma 2 to C1. But C1 is only allowed to use borrowed versions of gamma 2. This is similar to a technique that Perseus uses for its contexts. And then when it's C2's turn, we can take back ownership of gamma 2 and also bind the result to x. And so there's a problem with these rules, which is that borrows are allowed to escape their scope. So this program type checks, but it shouldn't. And to sort of see what the problem is, we can pull up our typing rule for let. And so we borrow x here. But this also means that we put x back into the owned context, and we also bind our new variable bx. But now we have both x and a borrow of x at the same time, which is not allowed. That's breaking aliasing XOR mutability. So we can fix that by adding this v-owned premise, which prevents the right-hand side of a let binding equals symbol from containing any borrows in it. This is what makes our downward-only language actually downward-only. And we also have to do that for thunks as well, because thunks are suspended computations. All right, so that was a borrow calculus without lifetimes, and it works as a language, but it's a little too restrictive. Like this downward-only restriction is a bit too much. So we make that more flexible by adding lifetimes. And for us, lifetimes are any totally ordered set with a successor function. We can sort of keep it abstract, but for example, like the natural numbers could be a set of lifetimes. And then our type system, we'll just put this little lifetime on our colon in our borrowable context. And this indicates alpha is the longest lifetime that you're allowed to safely borrow x for. So we update our rule. If you want to borrow at beta and x is able to be borrowed at alpha, then as long as alpha outlives beta, it's OK, which just means that alpha is longer than beta. So this is our outlives relation, which is greater than or equal to. And we also update this thunk rule in a similar way. So now thunks can capture some borrows, but only safe borrows based on this outlives constraint. And for the let rule, this is where we pick a lifetime alpha, and we stick it on the colon of all of our bindings in delta. And alpha also has to be basically a fresh, shortest new lifetime. So it has to be shorter than all of these things. And we just abbreviate this as alpha shortest instead of writing out the big inequality. OK, so that was lifetimes added to our read-only calculus. But it would be nice if we had mutable borrows. So I'm going to do that. This is our last type system feature. So we add this permission thing, which is either immutable or mutable. And we stick it on our borrow type. And we split our borrow context into two different contexts, one for immutable things and one for mutable things, where delta m is treated linearly. It's subject to context splitting. And for the borrow rule, we add these new contexts. And we look in the context corresponding to whether it's a mutable borrow or an immutable borrow. And then for our let rule, we have to split our context, our gamma again, because we have to decide which parts of gamma go into delta I and which parts go into delta m. And then we also have to split the pre-existing mutable borrowable contexts, because you can't have two different places mutably borrow the same variable. OK. So we've sort of beefed up our borrow calculus. So now it has both mutable and immutable borrows, and also lifetimes. And that's all I can go over with the type system. There is one more feature, lifetime polymorphism, that I'm not going to show. But we also support it. But now I want to go down a level in our abstraction stack and talk about our separation logic. So to start with, here's the usual frame rule from separation logic. It basically says that if a program runs without R, then it still runs with R, and R is unchanged afterwards. So it's sort of, your program is agnostic to whether R exists. So you can tweak this rule a little bit and turn it into a borrow frame rule. So instead of completely removing R from the top, you can just downgrade R into a borrow of R using a new shortest lifetime. And now this rule says that if a program runs with a borrow of R, it also runs with the full ownership of R. So it's agnostic to whether R is borrowed or owned. And this is like the temporary read-only permissions paper, again, has a frame rule like this, but without lifetimes. You can actually, for mutable borrows specifically, you can do something weird, which is you can turn the frame rule upside down, and you get this anti-frame rule, which says that if you have a mutable borrow of R, you can temporarily pretend to own R. And so this lets you break invariants temporarily. You can change the type of R. You can do whatever you want with it. But you have to promise that after you're done, R will be reestablished as an invariant. So it's temporary ownership. This is similar to a 2008 paper, Hiding Local State in Direct Style by Potier. OK, so that was both the type system and the borrow logic. And we don't have time for the semantic model, but I can conclude with a few things. So the semantic model. So we're still working on that. We're working on finishing a proof of soundness for the separation logic in terms of the semantic model. This has been taking a bit of time. It's actually been the hardest part of the project so far, which is not to say that the semantic model is really complicated. It's actually pretty simple, but it's a bit hard to find the right balance for all the definitions involved. So just kind of a balancing act of getting everything right all at once and getting all the proofs to go through. We also plan to use our borrow calculus as a source language for studying safe interop between languages that have borrows and languages that don't have borrows. This is part of like compositional compiler correctness things and type-safe interop and stuff like that. And in the future, we think that the borrow calculus could be extended to support different kinds of resources. And that would correspond to different memory models. So if your language has a different kind of memory model than our calculus, if we sort of abstract out the resources, then you could just plop yours in, and it would still work. And this is part of our hope that this borrow calculus could potentially be a platform for future borrowing research. And yeah, that is my talk. Thank you.
Okay, thank you, Brianna. I think we should line up in the middle for questions and come to this mic in the center. Okay.
Just wondering whether the class type checker bears any resemblance to the kind of rules that you're giving.
Yeah, so our rules are not necessarily algorithmic. So I think in theory you could build an algorithmic type checker for our rules, and I'm not sure if it would look similar to the Rust borrow checker. But our focus is mainly on sort of a theoretical model, so we haven't thought about how to actually implement like type inference or lifetime inference yet, for example.
Hi, are you sure you can't do non-lexical? Like, you don't seem that far. if you could just sort of say, we've left the scope, right? Is that
Yeah, so,
something
well,
explored?
so non-lexical, there's a lot of things that we assume that are specifically lexical, like our frame rule. This is a lexical frame rule, and our let binding rule is also a lexical let binding rule. If you wanted to go to non-lexical, you would probably have to start using capability passing for your lifetimes to sort of choose when to end it, like to end it arbitrarily, not just in a lexical structure. So I don't think it's impossible, but it is, I think, going to be a big change.
I have 2 quick questions. So the first one, I might have missed it, but are you formalizing this on paper or in a proof assistant?
It's currently on paper.
Okay. Are any plans for formalizing it, or?
It would be nice. We haven't thought about it too much because we're still very early on, so we haven't had time to think about mechanizing it. But it would be cool if it was mechanized.
Right. And then the other question was about, so this is supposed to be like a modeler thing where you can mix or you can choose which features you want to include.
Yes.
So how do you ensure that, well, if I just want the immutable borrows with polymorphism, that there's nothing of the mutable frame or a mutable thing that interacts with that? That it is actually modular, right? Your model.
If you just want mutable borrows with,
like how do you ensure that your model is still makes sense if you leave out some of the features?
Yeah, I think it would still be a case-by-case basis on the individual models. You have to prove soundness, that everything sort of works out with the features that you do have. We are going to, we break it down for like all of our systems, the type system, as well as the semantic model. We'll have like different versions of that for each sort of configuration. But if you wanted to do it on your own and pick a different configuration, then the idea is that it wouldn't be too difficult to do it, but I think you would still have to prove that the model is so good with that configuration.
So you still have to do some work. Okay.
I haven't thought about it too much, but I think that would be the case.
Would be nice, or would be interesting to see if you can automate that somehow, or
make it more streamlined.
Make it part of the model.
Yes.
Okay, I think we have time for one last question, but the next speaker, Sydney, I think, yes, come and start setting up.
Hi, so I'm Gabriel Radan from INRIA. Thank you very much. I like that because it looked like you did properly the theory of what we did for the half calculus in Kindly Bent to Free Us. And so it's sort of exactly like this. We build it.
Yes.
It was not clean at the end. One thing that I think is sort of missing in your borrowing zoo is the fact that you can have on the abstract both unrestricted and linear and affine objects. And it seems you don't really have this kind of objects in your calculus right now. You only have linear object and borrows. Is it something that you don't want to do? Is it problematic for the separation logic part, or what?
So you're asking if we could add unrestricted types more generally?
Sort of. Yeah.
I don't think there's anything preventing us from doing that. I haven't thought about it too much. So immutable borrows are like a special case of unrestricted things, and I think we could generalize that.
Yeah, so that's the thing. That's precisely, that was helpful to model immutable borrows, basically. You just delegate to that and it's done. So
yeah, I think it could be possible.
Okay, thank you.
Okay, let's thank Brianna again.